This is Just-in-Time Compilation Isn't Magic. My name is Doug Hawkins. Just a quick bit about myself. I work at Datadog currently. I work on our observability platform team. Basically, we make the internal APIs that our various products use to add observability probes into running applications for distributed tracing, security monitoring, things like that. You might wonder, what does that have to do with just-in-time compilation? Well, part of our goal when we're adding these observability probes is to be invisible. You don't want to have us increasing your overhead while we're trying to observe your overhead. That would be bad. So my job is to make those APIs, make tools for our product teams so that they know if they're adding too much overhead. They know if they're hurting optimizations that Hotspot's done, things like that. I also used to work at Azul Systems. I was a just-in-time compiler engineer there. I'm the creator of Azul Systems Ready Now technology, if you're familiar with it. And then, maybe more uniquely, as someone who's worked on the JVM, I was also a Java engineer for 10 years first. So I've been on both sides of the platform. I did a lot of stuff in bioinformatics, e-commerce, financial technologies, things that were somewhat performance intensive. So to frame our conversation for today, I like this quote from Arthur C. Clarke, which you're probably familiar with. Any sufficiently advanced technology is indistinguishable from magic. Well, in the compiler world, we talk about any sufficiently smart compiler is indistinguishable from magic. So our goal is to kind of surprise you, or to have you be able to use an abstraction and not think about what it takes to optimize it. Unfortunately, it's not magic. It doesn't always work out that way. And so what we're going to do today is kind of peel through a bunch of the layers that make up a compiler, not just Hotspot, but really any optimizing compiler. Kind of try to understand why they might fall over. What are they doing? What kind of analyses are they applying to your code? And where might they fall short? If you have ever bothered to look at compiler literature, it can sound a bit daunting. Like, there are all these terms, peephole optimization, static single assignment, interprocedural optimization, the list kind of goes on and on. We'll touch on a lot of these today. But I assure you, actually, many of the optimizations are straightforward. And there are just a few key concepts that kind of underpin the legality of a lot of these optimizations. Where I think it gets complicated is that they're layered on top of each other. One optimization feeds into another optimization, feeds into another optimization, and if one of those optimizations fails, the link can kind of fall apart. So that's what we're going to see. But I do have to tell you, this is just going to be a primer. I can't teach compilers in 40 minutes, I'm afraid. I don't even think I'm an expert. I'm honestly not sure anyone is an expert. There are just too many parts to our systems. Like, we're putting a Java virtual machine, which is this speculative, just-in-time optimizing compiler, on top of an operating system, on top of a hypervisor, on top of hardware that does its own speculations. I know I don't understand all those layers. That's okay. The aim here is really just to demystify, show some of the common optimizations, explain the key concepts, and provide a jumping off point if you're interested, and some tools as well. Now, what I'm mostly going to talk about today is going to apply to really any optimizing compiler. It could be C, it could be C++, it could be Rust. Okay, not Go, its optimizer's not great. Definitely not PHP, but a lot of languages. These things apply. But let's first talk just a tiny bit about what makes Hotspot kind of special. It is a just-in-time compiler. So what do we just-in-time compile? Well, let's take a simple example. There are example references in the lower right-hand corner. You can go on GitHub and play with them afterwards if you're so inclined. But we're going to start with this. Let's look at the middle first. There's this inner loop. It's allocating 1,000 objects. And we're measuring the performance of this inner loop by calling system nanotime before and after the loop. And I'm going to do that 500 times. Now you'll notice there is this funny thing here. I have this global variable that seems to kind of be superfluous. It's not quite superfluous. What happens if I run this? Well, I get something like the column on the left here. The left number is the chunk number, and the right number is the time in nanoseconds for allocating 1,000 objects on this laptop. So it starts off at around 35,000-ish nanoseconds per chunk, give or take. After about 70 or so chunks, it speeds up to about 16,000 nanoseconds. And then if I wait a little longer still, after about 200 chunks, it drops down to about 5,500 nanoseconds. This is the just-in-time compiler kicking in. And as of Java 7, there are 2 just-in-time compilers. There were always kind of 2. They were used for client and server before. Now they're used together. But after 70 iterations, the first just-in-time compiler, C1, kicked in. We switched from running in the interpreter early on to running in machine code. And then, if we run a little longer still, this is really hot. It's worth putting even more work into optimizing it. A second just-in-time compiler kicks in called C2. Very inventive naming, I know. That's what they're called. And that's when we get to those numbers. And for an individual function, it really is a step function like this. It's just phase transition from interpreter to C1 to C2. You can imagine across thousands of compilations, thousands of methods in your system, you get more of a smooth curve. But for an individual function, it really is a step function. And this is where hotspot gets its name. It's called that because it compiles hot spots at the granularity of methods, or actually in the case of the prior example, loops. You might have heard the truism, you spend 90% of the time in 10% of your code. I can assure you that's wrong. It's more like 99% of your time in 1% of your code. It's vanishingly small. And all we need to do is cast a big enough net to find those critical methods, compile them, and you'll get pretty good performance. So what we saw before was C1. It's the first JIT. Its job is to trigger early 2,000 method invocations. There's just a counter for every method. We count how many times it was called, or 60,000 loop iterations inside of that method. It compiles fast. It doesn't do a ton of optimization. It's just to get us from interpreter to machine code quickly. It produces relatively slow code. Its goal is to compile fast, run slow to get us kind of going. Gives us quick warm-up. C2, on the other hand, it's our second JIT. It triggers after 15,000 invocations of a method or 100,000 loop iterations. It compiles much slower, 4 times slower on average. But it does do more optimizations. It produces faster code, about 2 times faster. You're like, wait, 4 times as long to produce code that's only twice as fast? Yeah, that's how optimization is. It takes more and more work to get closer and closer to optimal. But C2's goal is to get us to peak performance. So why did I have that funny variable? What was it for? Well, let's take it away and find out what happens without it. These are the numbers you get. After it was about 300 iterations, we reached C2, but we're getting very suspicious looking numbers. 100 nanoseconds, or sometimes 0 nanoseconds. I mean, modern hardware's fast, but I think 1,000 objects in 0 nanoseconds sounds a bit implausible to me. What's going on here? Well, without that global variable, nobody's using that object. Nobody can use that object. By putting in the global variable, I've created the potential that somebody else in the code somewhere could go to that global variable and retrieve it. Without that, nobody's using it. So we don't need it. Okay, and it's inside of a loop, which is now an empty loop. Okay, so 1,000 no-ops or 0 no-ops, doesn't really matter. Let's just get rid of the loop, too. The whole thing goes away. So what are you measuring? Nanotime? Call followed immediately by calling nanotime. That's what you're measuring. Okay, so why sometimes 100 and sometimes 0? Well, on Windows, the accuracy of nanotime is 100 nanoseconds. So if the clock ticks forward, you get 100 nanoseconds. If the clock didn't tick forward between those two calls, you get 0 nanoseconds. It's great fun. It's going to be a little bit different on Linux. Even running the Linux subsystem on this laptop, you get like tens of nanoseconds. It's got a little more precision. But yeah. And this is one of the things that makes benchmarking Java fun. You could measure absolutely nothing. I've seen people do it. It's great when you have to explain to a customer, I'm sorry, you're not measuring anything. Okay, so now we know what gets compiled. Let's talk about some optimizations. We're going to start simple, almost insultingly simple. This is an actual optimization. 2 plus 2 equals 4. In compiler speak, we give it a fancy name. We call it constant folding. We have a constant, a binary operator, a constant. We can turn that into another constant. But that is an optimization. Now let's think a little bit about how we might represent this. So in Java, we use infix notation, so we would write 2 plus 2. What's going to happen inside of Java C, your Java to bytecode compiler, is it's going to turn that into some sort of what we call abstract syntax tree, AST. You can imagine the root of your tree is the plus operator, and then the left branch is the left-hand side, and the right branch is the right-hand side. We break the whole program down like this, and we can process that tree. There are extraordinarily slow interpreters that just walk ASTs. You would not be surprised that IE5, that's what it used. Just AST walking. But maybe we should use a different representation. If you think about this AST, it's not that different from Lisp. It's kind of a prefix syntax, right? Plus 2, 2. That's Lisp. Or we could flip it the other way around. We could use reverse Polish notation. If any of you are as old as me and used HP calculators that are stack machines, they use a postfix. You would do 2, push it onto the stack, 2, push it on the stack, plus pop both operands from the stack, push a new result onto the stack. It's actually what hotspot does. So in Java bytecode, this is iconst 2, I add. So postfix. All right. Now, how would we implement the optimization on top of that? We could. Well, we could just look at this as a pattern. It's a const, followed by a const, followed by a binary operator. This is just a regex. The reason we call these peephole optimizations is because they look at a small window of code, and if it matches the pattern, we apply the rule, and that's it. Now, how many of you have ever written a regex to process some file? Right, and how many of you handled every single input the first time you wrote that regex? No, nobody raised their hands. Good, I would call you a liar immediately. No one has ever managed to do that. Well, which one did you handle? You handled the ones that were in the file you were dealing with. Then you got a new file, and you're like, oh, great, now I have to remember what that regex did. And update it. Compilers are kind of the same. It's hard to cover every permutation, every possible pattern that could come up. So what do? We covered the popular patterns first. If you think you're special and you like to write your code a little bit differently, we might not have covered your pattern. You might be better off sticking to something a little more idiomatic, because whatever the most people are doing, that's where we get the most bang for our users by optimizing it. And just to illustrate this, Java 9 introduced a new, or Java 10 introduced a new indefined string concat. I think it was 10. But prior to that, it was done with string builders. So you would write something like greeting plus username, but what was actually output by Java C was something like the second line there, return new string builder greeting append username to string. Okay. You could write that yourself if you really wanted to, or maybe you could write the thing at the bottom, builder equals new string builder greeting, builder append username, builder to string. Like these are functionally identical. Surely they execute the same. No, I'm afraid not. There is an optimization hotspot called optimized string concat that very specifically recognizes the bytecode produced by concatenation and nothing else. So, if I write the thing on the top, it will run in 12 nanoseconds on average on this machine. If I write the thing on bottom, 21 nanoseconds. Sure, it's nanoseconds, it's small, but you can see, like, this small, seemingly insignificant change, and the whole pattern matching thing just kind of falls apart. But I think the real magic to optimization is the fact that we start to compose them together. So let's take something mildly more complicated. 2 times 4 plus 1, 9. How would we optimize this if we were looking at it at a bytecode level? Well, this would be iconst2, iconst4, imul, iconst1, iadd. So you read them top to bottom, you're pushing them, popping them from a stack. So we look at those first 3 instructions. It matches our pattern. Constant, constant, binary op. We have our window there. We can turn that into a new constant. There's no special constant for 8, so we have to use a byte as an integer push 8. So now we have by push 8, iconst1, iadd. Oh, if we look at that as a window of instructions, it still matches our pattern. Constant, constant, binary operator. Let's apply the same optimization again. Now we get by push 9. And this is what happens. We're going to start to compose optimizations together. What happened in the prior example? I confused it because I put the builder into a variable. It wasn't expecting that. This would get optimized by Java C. And this is where I have a bad joke that I like to use all the time. Surprise, surprise, optimization is an optimization problem. Optimizers aren't actually optimal. That's not actually even really our goal. Compilers are just aiming to be sufficiently smart. Sufficiently smart for whom? I don't know. That's up to each compiler to decide. Fortran has decided to be really good at scientific operations. Java's really good at dynamic dispatch. There's nothing wrong with either choice. It's what their communities need. Our aim is actually just to make most programs better with one key caveat, while not making other programs worse. Like, we don't want to do something that's going to make one program way better and make another program way worse. That might not be a good trade-off, because we're not serving just, you. We're serving you and you as well. So it's got to be good, pretty good for everyone. Let's look at some other simple optimizations. This is stuff that Java C can actually do. So I've got this hello propagation example. I have a constant message that's just hello world, and I print out message inside my main. I could use a tool that's packed with your JDK called Java P to disassemble this to bytecode. If I do that, I'll find that message is still there, but message is not mentioned in main anywhere. It just has a single line that says load constant hello world. Doesn't refer to message. It's an optimization called constant propagation. Just take the right-hand side of the constant and copy it over there. That's all it is. There is also a constructor, even though I didn't write one. That's an empty constructor in the middle, if you were wondering. And we could compose some optimizations too. I could have, say, a constant greeting and a constant addressee, concatenate them together, and at compile time, Java-C would optimize this to just a single constant, load constant, hello Devnexus. So it's propagating two values, realizing that after it's done that, it's got a constant plus a constant that matches our pattern from before. We can fold that together into a single constant. Make sense? Yeah. And that's actually about all the optimizations that Java-C does. It really does not do much. As of 1.4, when Hotspot was introduced, they deprecated the optimization flags inside Java-C itself and said that's the runtime's job. That's the just-in-time compiler's job. Java-C doesn't do much at all. There used to be an O flag for Java-C, but it really doesn't do a lot. All right, now some small but not so simple optimizations. There are these things called intrinsics. They're basically magic functions that just behave in otherworldly ways. So let's say I'm copying an array of 1 million random integers. You can imagine what that function looks like. Okay, I could do it one of two ways. I could create a copy and I could do system array copy. You ever looked at system array copy signature? It's insane. Object int, int. What? Well, object is the only common base class of all the array types, so that's why it does that. But like, how could you possibly optimize this? Well, at least in this context, we can actually say both arrays are typed integer and we could optimize. But maybe it would be better to say, just do a simple C-style loop. I could create a new array, and I could just copy all the elements. That will be slower, at least in the beginning. Why? Well, the one at the bottom starts off running in the interpreter. The one at the top doesn't. System array copy is, let's say, used occasionally. So it has been very carefully optimized. As soon as the JVM starts, it will create a version of system array copy specialized to the microarchitecture that it is running on. Some poor JVM engineer has had to go and write machine code for the Intels from today, the Intels from 5 years ago, the Intels from 10 years ago, the Intels from 15 years ago, and has made one that is optimal for all of those different microarchitectures. And it's going to be used. So we just effectively JIT it immediately. There's no reason to wait. We know it's going to be used because it's used by the standard library. So at least the first time, it's going to run in like 1.9 million nanoseconds for a million versus 4.2 million nanoseconds. Now, the one on the bottom, given enough time, it will get JITted and it will perform just as well. But there are these magic methods that have magic properties. So these are specially handled. There are often common operations like arrays, strings, crypto algorithms even, because we can take advantage of the hardware. They're often vectorizable with custom hardware stuff, single instruction, multi-data instructions, if you're familiar with those. And they are frequently hand-rolled assembly. They can be other things too. These used to be really hard to find. As of newer JDKs, there's now an annotation called intrinsic candidate, where they go and flag things that they think, oh, we should intrinsify those if we haven't already, or if we have, we mark them as well. So you could go search your JDK if you really wanted to and find these. They're, I think, close to 100. I don't even know. All right, so let's look at some slightly more complicated things. Code elimination, which is what we saw in the beginning, right? We saw an object just completely disappear. I took a compiler class in college. We did exactly one optimization. This was it. It's called common subexpression elimination. It's not complicated. It's just if a equals x plus y and b equals x plus y, could we just put x plus y in a temporary variable and then assign a and b to the temp? Well, is this a valid optimization? That's a question I want you to ask yourself. Like, is this valid for local variables? Is it valid for member variables in an object? Is it valid for member variables in an object if they are volatile? The answer to those questions is not all the same. That's what the compiler has to do. It has to enforce the memory model and follow the memory model. So let's take a slightly more complicated example. Int x equals 10, int y equals 5, return x plus y. Okay, this returns 15. I don't know why anyone would write it this way, but you could. Javac will not optimize it. This is too complicated for Javac. I did check the bytecode today. Okay, but you can imagine how a compiler could do this. We have a 10, we push it onto the stack, we store it into our first local variable, let's call that x, so x is known to be 10. Do the same thing for y. Load x and y back from stack. They are known to be the constants 10 and 5. Okay, we could fold those together into 15. This is completely doable. Takes a lot of reasoning by the compiler to track all of these values, but it's doable. And maybe you can see after you've done this, well, I don't really need x and y anymore, do I? Those are what are called dead loads and dead stores. We can just get rid of them. We don't need them. We have our answer. And then there's another fundamental optimization or type of optimization called code motion. Say A equals x plus y and B equals x plus z. Can these switch orders? Is that legal for local variables? Is that legal for member variables? Is that legal for volatile variables? Again, the answers are not all the same. But generally speaking, this can be done. Now we could do loop optimizations too. These are the, getting to be the big ones. So let's say I have two vectors of size 16, and I want to create a summation of those. So I just write a loop over 0 to 16 and sum them together. Would it be faster to say, do these 4 at a time? Modern Intels actually have the ability to execute 4 arithmetic operations simultaneously, not even using the special invector instructions. So you want to take advantage of that. So maybe this is good. So maybe what I do is I move my stride to 4 at a time, and then I do I plus 0, and I plus 1, and I plus 2, and I plus 3 all at the same time. Perfectly valid. That might have been really good on old hardware. Maybe not so good. Maybe we could do better on new hardware. Well, fortunately, a lot of compilers have the opposite, not hotspot to my knowledge. They have loop re-rolling. Like, what? Yes, it will actually take an unrolled loop that someone wrote by hand and be like, nah, I'm not sure you got that right. Let me turn that back into a regular loop, and then I'll reevaluate. Like, why would you do that? Well, remember, your programs are just, text to us. It's just input. So what do we do with your programs? We normalize them into a form that's easier for us to work with. So we're going to take your messy loop, and we're going to put it into a form we like, and then we'll put it back into the optimal form later. But we will, second guess you all the time. So this is really just data normalization, input validation, if you want to think of it that way. You probably don't think of your programs as inputs, but that's what they are to a compiler. And then fancy sounding things, loop invariant code motion. Basic idea is if there's something that's not changing inside the loop, there's a value we keep reloading again and again inside the loop. Do we need to do that? Or if there's a test that's always true, do we need to do that? Maybe not. So we could take I less than array length. If we know that the array doesn't change, we know that an array's length can't change, then we could just store that into a local variable, compare against that, and be done. And again, I'll ask, what is this valid for? local variables, member variables, volatile variables. What if there's a call inside the loop? Have you ever thought about that? How would that affect it? These are the types of questions the compiler has to be asking. So what it does is it takes these programs. What we've seen so far are just very simplistic things. They're what we call a basic block. A basic block is instructions with no control flow between them. So let's take something a little more complicated. Int x equals something. If some condition, we go left, x equals 10, else we go right, x equals 20, y equals x plus 10, right? We turn this into a control flow graph, we end up with a diamond like this. Each of those nodes is a basic block. We can do the same thing for a loop. We'll turn it around a little bit. We come into the initialization block, I equals 0. Then we go into a block that's the test, I less than 10. If it's true, we go into the loop body followed by the increment step, come back to the test. If it's false, we go out the other end. So we turn it into this control flow graph. If you've ever looked at any compiler stuff, you might come across the terms local versus global optimizations. These are probably not what you think they are. These are not global to the program. A local optimization in compiler speak is local to one of those tiny basic blocks. A global optimization is one that's across basic blocks, one that crosses control flow boundaries. So you would think like local is about an entire function. No, it's not. It's about like a little fraction of one function. And then the real magic to me of compilers is this thing that sounds intimidating, static single assignment. This was research in the late 80s, became popular in compilers, kind of starting with Hotspot, which was built in the mid-90s. And what it does is it actually versions your variables. Like, what? And assigns them once very much in quotation marks. Like, how does this help? Well, let's apply it to the example from before. X, if we go down the left path, we have x version 1, it's equal to 10. We go down the right path, we have x version 2, it's equal to 20. And then when we come back together, we say we have x version 3, which is a logical merge of the values of x1 and x2. Like, why? This seems complicated. And then y0 is the result of x3 plus 10. But I assure you this does actually make a lot of analyses much easier. Let's apply a little bit of reasoning to this. So now we can say, down the left branch, we're going to do right-to-left type inference. It turns out the compiler always did right-to-left type inference, even before Java 10. Most of the type information isn't even in the bytecode, so we were just making you type that for fun. It was great. But the compiler does right-to-left type inference. So x1 equals 10. The type in the compiler's terms is a set of theoretical values. For numbers, it's a numeric range. So it's the set of the range 10 to 10, i.e. it is the number 10. x2, on the other hand, is in the range 20 to 20, i.e. it's 20. So now you can start to see how that merge might actually be helpful. We have x1, which we know to be 10 to 10, and we have x2 that we know to be 20 to 20, so we can now say x3 is in the range 10 to 20. We could try to more precisely model that it's the set of 10 and 20 and none of the values in between, but no, it's just a range. And then from that we could say y0 is 20 to 30. And then if there was a test, like is y0 greater than 0, we can now definitively say, yes, y0 is definitely greater than 0. So each of these analyses creates new possible opportunities. Might not pay off, but they might. And we can do the same thing for loops. So we could say I0 is 0. Then we can come down to the bottom and say I2 is in the range 0 to 9 because it's clamped by being less than 10. And then we could say I1 is in 0 to 10. It is the merge of the entry in the bottom of the loop. When we exit the loop, we know the value would be 10. This sort of inductive reasoning, which is so-called from your math classes, base case, induction case, is important to eliminating array bounds checks. So we can do all sorts of interesting analyses. And that's really what static single assignment is about. It's making all these other analyses easier. Let's apply it to some of the examples we saw from earlier. If I have x0 and y0, and I know that my computation is just using those versions, then yes, this is the same computation. I can common these two operations together. And this becomes a slightly different optimization called global value numbering. So called because what we're actually doing is just hashing the computation. I know that sounds weird, but that's what the compiler does. And so now we can reuse that computation if we so choose. And we could do it across basic blocks, not even just within a single basic block. That's why it's called global value numbering. Same thing with code motion. If we saw that a sub 0 depends on x sub 0 plus y sub 0, and the other one depends on x sub 0 plus z sub 0, their common dependency is x sub 0. As long as x sub 0 is done, they can happen in either order after that, which is good because the hardware can actually do these two adds simultaneously. The hardware does the same analysis, believe it or not. And you could even apply this to something like loop unrolling as well. You can imagine, in a way, taking like sum from 1 to 100, which is 5,050. We could unroll this into sum 0 equals 0, sum 1 is equal to sum 0 plus 1, on and on and on. We can constant fold all the way through all of these versions to get 50-50. That's doable. And then once we've done that, do we need any of those versions of sum anymore? No, they're just gone. Do we need the loop anymore? No, it's just gone. We just return a constant. Entirely doable. Hotspot doesn't quite manage this, but many compilers could. So what SSA is actually doing is it's doing dependency analysis. It's figuring out that this computation must follow this other computation. If one computation doesn't need to follow the other computation, guess what? We're free to put them in whatever order we feel like. There is really just one hard rule. Assuming there are no other threads, and we get to assume there are no other threads, that is the compiler's viewpoint, code motion and code elimination can change they can't change results in this thread. So they can move things around however they feel like, based on the dependency analysis. What those keywords, like synchronized and volatile, are actually doing is they are adding restrictions on code motion and code elimination. Volatile says, you can never get rid of my load. Volatile says, you must keep my loads in this order. Volatile says, you must keep my stores in this order. So you just can't get rid of things that you used to be able to get rid of. Synchronized also introduces a happens before, which you can think of as a dependency. There are ways to preserve order in one thread so that you can reason about it in another thread, because without them, there are no rules. And the way the compiler does this, I think is really cool. Okay, this is getting a little deep, but I think it's cool. So if you think about what's happening, like if I'm loading from, say, p.x, p.y, I can think of that as a load operation from a point in memory, right? I do an address computation, I load from memory. I load those into some registers. As long as I know that memory hasn't changed, in this thread, then I can use that value again. And that's where things get fun. What if there was a call in between those two things? Could that call change memory? Could it somehow have a reference to the point object through some global variable somewhere and change p.x? Yes, it could. And then the optimization becomes invalid. The way the compiler actually models this is it creates sort of a nonce state of memory was in this state before the call, memory is in a new state after the call. If we're loading from two different memory states, then I have to reload. If we're loading from the same memory state, I don't have to reload. So if you've done any like purely functional programming, this is kind of a familiar concept. This is applying purely functional ideas to a not at all purely functional language. And this is where things get fun. So I have something like array.length. Where is array coming from? If it's coming from heap, could it have changed if there's a call inside the loop? Yes, it could. That means it's no longer guaranteed to be loop invariant. So now I can't do some of those cool loop optimizations I saw before. The lingo in Java in compiler land is compilers must be conservatively correct. We can't break any rules that you've agreed to. Now, you've agreed to letting us move your code around, eliminate code. You may not have read the Java language model, but that's what it says. You've agreed to that. But we can't break it for a single thread if there's a call like inside this loop. The way I like to explain this is that from the compiler's perspective, a call is a Pandora's box containing all the evils of the universe. We have to assume you could have done anything. You could have changed final variables using reflection. So even if array was final, I can't optimize it. Really, really annoying. We did actually implement this optimization while I was at Azul. I could explain how that works, but yeah, you can do all sorts of horrible things. Anything in the heap can be modified. Any final variables could be modified, except there are two exceptions. Static finals, you can try to change them with reflection. We're allowed to ignore you. That's in the standard. You agreed to that. And local variables. You can't change local variables. Once you put it in a local, it's OK. In Python, that's not even true. There's a reason Python is really hard to optimize. So we need a way to open this black box and see that there's nothing evil inside. And that's interprocedural optimization. This is closer to what you probably thought global optimization actually is. And the main way we do this is called inlining. It's conceptually quite simple. Say I have a call to square. This is the implementation of square, if you were wondering. And we pass it 7. OK, we can take that 7. We can constant propagate it into the function. We can then constant fold it. And then we don't need the call. So basically what we're doing is copying, pasting, and then substituting the parameter values in at the call site. And so we get 49. And if you want, you could run with these options. And you could confirm that when that hot method gets compiled, it inlined square. That happens. Now we've opened the black box. We can see there are no memory effects. You do this inside a loop, you get to keep all the loop optimizations. Cool. The problem with Java is it's a dynamic language. I know you're like, no, it's not. But from my perspective, it is. All the calls are dynamic. Classes are lazy loaded. Classes are lazy initialized. You create classes out of thin air with Hibernate and serializers and deserializers. It's a pain to optimize. It's not as bad as JavaScript, but it's not easy to optimize. And collections are type erased. So what are we to do? Like if we see something like this, map, string, string, new hash map, map put, well, map put is map put, not hash map put. We don't know exactly which one we're calling, right? Well, this is where the compiler can help out again. I'm not going to go through this whole thing, but you can imagine, because we do right-to-left type inference, we know at the new call, it's exactly a hash map. We know it's not a subclass of hash map. We know it's not some other type of map. It's hash map, exactly. So when we get to the call down here, that invoke virtual of map put, we can use the type reasoning to say, oh, well, really, it's just a direct call to hash map put. We don't need to do that. And now we could say, OK, it's a direct call. I could inline that. Unfortunately, hash map put is too big, and it will refuse to inline that. But in theory, we could. And maybe in an ideal world, we could even say, like, key, even though hash map is taking object-object because it's type erased, we could say, oh, the key is really a string. In fact, we know it's a specific string literal. And so when you call hash code inside a put, we know that you're calling string hash code, not object hash code. It can apply that sort of reasoning. And this is why, to me, I think inlining is really the key. Not just because it eliminates calls. It does do that. But calls are actually really fast on modern hardware. But because it creates new opportunities. We can say, oh, we can take the exact parameter information and use it to do other optimization, like constant folding or turning indirect calls into direct calls. But also because it preserves opportunities in the caller as well, we can look and see, oh, you're not changing that part of memory. We get to keep some of the loop optimizations surrounding the call. And Hotspot excels at this. It has many strategies for inlining. I think there are like 5 or 6 different strategies. Static ones, dynamic ones. It will do 9 calls deep. It will do 2 dynamic call sites based off profiling information. Basically, if you keep your methods relatively small, it'll probably inline them. I say that as a person who spent a lot of time debugging inlining problems, and I've had to look at inlining trees and compare them where it's like 200 methods inlined into a single compilation. You don't want to do that yourself, but Hotspot will gladly glom them together for you to find new optimization opportunities. But the truth is, I can't really give you an easy answer as to what you should do, because optimization is hard. Optimizers aren't, in fact, optimal. They're just conservatively correct and sufficiently smart, as the lingo goes. The pattern matching can be brittle. Optimizations build on top of each other. If one fails, the whole thing can kind of come crumbling down. It's kind of a house of cards. Like, one missed inlining opportunity can cause a lot of things to fail. So what are you supposed to do as a developer? Well, don't sweat the small stuff. Like the small optimizations, like 2 + 2, we got that. And thank you. You should be very, yeah, we can do that. Those will just work. Just identify your hotspots and focus on those. Where we fail is bigger things. Object elimination is actually hard. Probably not going to work most of the time. You know, put in a single global variable and it stops working. But we do now have a lot of good tools that you can leverage. So there's Java Flight Recorder, if you want to use that. There's Java Measurement Harness, which will help you write micro benchmarks and try to avoid dead code elimination that invalidate your benchmarks. And there are tools like JIT-Watch that will show you what the JIT is doing. They'll show you the inlining. You can even see the assembly if you're so inclined. So really, the only thing I can tell you is no one is truly an expert. Basically, just don't assume. I think part of what happens with optimization is people think it's magic, and then they just use it as a justification for whatever they want to do. It's like, oh, we can't do that, performance. Oh, we have to do that, performance. Like, because nobody feels like they understand it that well, then they just like use it as a unassailable argument to do whatever. No, what you have to do is just measure, profile, and check everything. You really don't know. It's a situation where works on my machine might literally be true. It might work on my AMD, but not my Intel, or it might work on my AMD, but not my ARM. You have to check. And so, with that slightly sobering note, I hope you learned something about compilers today. Thank you. If you want to go check out the examples, please do so. And thank you all for coming. Yes?
Is there a way to summarize how all this changes for purely functional language?
Mostly I would say it doesn't. Like, hypothetically speaking, it should be possible to do much better for a functional language than a non-functional language, especially if it were purely functional. Like, there are theoretical ideas that you can make a much better garbage. Yeah, theoretically, you could make a much better garbage collector because you don't have to worry about old objects pointing back to new objects and so forth. In a purely functional language, only new objects point to old objects, not vice versa. So there are a lot of cool things that you could do, but the reality is we optimize what's popular, and purely functional languages just aren't popular enough. So we're really good at Java and JavaScript, which are hard, and not so good at OCaml, which in theory should be easy. Yes?
You were talking about functions like addition, multiplication.
Mm-hmm.
You have constant behaviors, predictable behaviors.
Mm-hmm.
What about random? For instance,
Oh.
Fortran, if you typed in random
Mm-hmm.
5 minus random 5, it would optimize it to 0.
Yeah. Yes, there are some fun ones where, like, yes, theoretically you could optimize random ahead of time. To the best of my knowledge, Java doesn't do that, but yes, it's valid.
Is there a way that they flag functions to indicate whether or not they have particular
So in some languages, the answer to that is intrinsification. They're kind of directives to the compiler to behave a particular way. So like examples that are easier to are kind of the other way around. Like you could think like, I'm calling the PID function. It's a program ID. It returns an integer, theoretically from memory, but I know that it's actually coming from the OS. It's not supposed to be touching any user land memory, so I can kind of assume it has no side effects on the rest of the program. Or malloc is supposed to only return to me a new pointer, so I get to assume that it doesn't touch a pointer that I already hold. So, mm-hmm.
So, looking at all your examples of kind of for loops and all the ways that you destroy optimizations for simple for loops, I'm like, oh my god, I'm writing all this stream code. Like, has Hotspot started to grow some optimization?
Well, so that is the thing, is like regular arrays and collections are honestly going to perform better because we've had 15, 20 years to optimize them. Streams, we haven't had nearly as long to optimize, and there are more layers to peel through. They're popular, so they're worth spending time on. My company was very much spending time on optimizing them, but you know, it's essentially you're trying to reach parity with the thing before, but it's probably not going to be better than the thing before. So yes, in like the code I do, we worry a lot about performance in lots of places, and you know, like at one point people were debating, oh, should I be doing concatenation this way or that way? And I'm like, what you should actually do is just take the stream out. But it really only matters if that's the hot part of your code. So first thing is always profile. Like if you've got something that's really the core of your program that needs to perform well, then yeah, maybe you have to forego some of the abstractions. Most of the places use them, they make your life easier, it's fine. Mm-hmm.
For the hardware intrinsics, does it base what intrinsics it can use on the CPU it's running on?
Correct.
Or the CPU architecture that was targeted with the JVM?
No, well, a little bit of both. I mean, obviously the JVM was built at a particular time with a knowledge of particular pieces of hardware, but it does feature sniff your hardware and decide what to use based on all the options it knows about.
So is it the minimum common between the two?
Yeah, that's what it would be. But yeah, this gets really fun. Like, okay, this is a little just nerdery, but running on hypervisors can be fun because sometimes the hypervisor, they didn't think of what they were doing. So the sniffing direction will tell you what the underlying hardware does, but then the hypervisor hasn't actually implemented those instructions. So it tells you it can do one thing, but it actually can't do it, and then the JVM blows up spectacularly. It's great fun. Yes.
With stuff like Project Valhalla, is that going to affect the kind of optimizations that compilers can do?
I haven't kept up with it too much, so I don't feel like I'm very qualified to answer that at this point. I'm sorry. Yeah, joys of my day job are I have to support like Java 7 and 8, so you know a lot of these things are off limits to me. Yes.
So just to be clear, most all of the things you showed us today as far as optimization, that's all happening in just in time compiler?
Correct.
I do not suspect.
Yep. Yes.
Follow up to that, are any of these optimizations in ahead of time compilers?
Yes. So a lot of them are, pretty much everything I covered today is, because all of the stuff I covered today is primarily based on static reasoning. But there are optimizations, and this is one of the secret sauces of Hotspot, that are really based off of profiling the application. So you can imagine data flowing through a dynamic call site. Sometimes you can statically reason about it. Sometimes you can't. There might be, and so what it's actually doing is when you're running in the interpreter or C1, there's extra pieces of code running that are keeping track of which types went through this call site. And so the hope is by the time you reach C2 and you're hot, you know which ones are the most important, and you can then turn those into direct calls and maybe even inline them. And that's something that's hard for just a ahead-of-time compiler to do. You need what's called profile guide optimization. Now you can do that as an ahead-of-time step, run it, gather a profile, and then feed it back into the compiler again, and Graal will let you do that. But at that point, you are having to compile, run, gather a profile, compile again. So that can be kind of complicated for deployment. So.